So yeah, you can see I've set the domain for you. Hopefully it makes sense why I have that domain. And I realize that at one point I think we're going to kind of go off the top of the graph, just kind of how it worked out. So it's okay. See if you can graph this, and then we'll investigate it a little bit further and talk about tangent lines and try to make some connections with this new stuff and old stuff. McKenna, what is up? The table is good. So when you plug those t values in to the x equals root t, you should get 0, 1, 2, 3, 4. Make sense? Okay. And then the y's would be 1, 2, 5, 10, and that's the one that'll probably go off the top, 17. Does that all make sense? Okay, so literally, I mean, I know this is new and everything, but let's not overcomplicate it. It really is just input-output. You just have kind of a different input-output looking scenario than what we would have had in the past. And then from a graphing perspective, this is just plotting points, which you're all very good at. Two, 5, 3, 10, I guess would be up there, and 4, 17 is going to be just about off the top of the page up there somewhere. And just like using your math-trained eyes, what does this kind of look like to you guys?
X squared.
It does kind of look like half a parabola, right? So I'd say that would be a pretty reasonable looking graph. Did you guys eliminate the parameter yet?
Yes.
To do that, did you square the x equation, or did you subtract 1 from the y equation? Square. I think that's probably the easier way to go. So that would give you x squared equals t. And then by substitution, that would give you y equals x squared plus 1. And then when you do compare that, when you look at what resulted from the eliminating the parameter of t and looking at the graph, you realize, hey, that thing is just a parabola. We got the right half of the parabola, right? In order to get the left half of the parabola, what would we need to do with our parametric stuff? How could we get that left half to show up?
Add more values.
Specifically, what kind of values?
Negative.
Yeah, negative t values. Yeah, so if you had negative 1, negative 4, negative 9, negative 16 for your t's as well, then that would, or would it? Yeah, square root, huh? You see what I'm saying? Yeah, this is a little bit different. So, do you see how parametric stuff is, even though there's relationships there, it's its own thing, right? We can't just be like, oh yeah, I can just eliminate the parameter, no big deal, and that'll always work for me. In this case, it really wouldn't work for you, would it? Specifically here, based on these parameters, you can really only get the right side. You really can't get the left side because of the square root of t thing. So, food for thought. Make sense? Okay. Let's do one more. You can graph it on the calculator if you want. We already did quite a bit of that yesterday, so I think we'll forgo that for the moment. Let me think here. There's two more. I'm okay with... Let's do this one. Let's do number 3. And you know what? Can we agree on number 3? Can we agree on exactly which t values we'll use? I mean, the domain is -2 to 3, so it should be pretty straightforward. But let's, I think, if we go -2, -1, yeah, these will all fit. 0, 1, 2, 3. Let's just go integer values on that. So let's all just use those inputs just so we all have the same numbers, and hopefully it'll all make sense. So go ahead and create your table, and let's get that graph up there, and we'll talk about, if we have an opportunity, we'll talk about some calculus stuff to go with it. So far, this is no calculus at all, right? Did you guys do parametric stuff like in pre-calc? I know I've talked with him about that, because this is like, right now, so far, nothing has to do with calculus, right? It's just a different way of graphing things. So I've encouraged him a lot to consider. you guys think?
Oh, I didn't know that negative 2 was in there. I didn't know if the-
Yeah, I thought negative 2 was part of the,
Well, I think, you know what?
yeah, I just did 2 over 2.
I think I did the same old thing, I think. Because that's part of the domain, right? Oh, let's fix it. Goodness gracious. So just t over 2. It's still going to have fractions, right? We're just going to have t over 2. You know what? I did the same thing. I should probably put that in brackets or something. Okay. Let's try it again. So let's see here. This would be negative 1.
X, do you get square root of x plus 2 over 2?
0.
What should we do? Do 2y?
Right.
I'm not sure. Do 4y
Is that better?
plus 2? 4y squared plus x plus 2. 4y squared
No?
plus 2.
That sounds good.
4x plus 2 just
I think it's good. I just put them all over 2.
divided all by 4 is
I didn't subtract any 2s. Okay. There we go. Okay, you guys good? I know I'm good now. All right. So from a graphing perspective, let's see here. 2, negative 1, oops, and negative 1, negative 1/2, right there. And then negative 2, 0 is right there. And then negative 1, positive 1/2 would be right about there. 2, 1 is there. And 7, 2, 4, 6, 7, 3/2 is right about there. That look good as far as the dots go? Kind of looking like a sideways parabola now, isn't it? Okay. So if I trace through to there, and I'm going to put my arrows indicating the direction of motion, something like that. That could be a graph of this parametric. A couple things to point out, a couple questions, I guess, for you. Do you guys see any horizontal tangent lines on this graph? Horizontal tangent lines. And let's break this down. Horizontal tangent lines would be where the slope of that graph is 0. Do you see any 0 slopes? I'm not talking about projecting it out into the distance. I'm talking about right there. Any horizontals? I don't see any horizontal tangent lines either. Do you see any vertical tangent lines? How many do you see? Yeah, wouldn't there be one on the far left side? And of course, a vertical tangent line happens when the slope of the tangent line is undefined, right? And the denominator is 0. Okay, good deal. All right, so if you eliminate the parameter on this one, what'd you do? Multiply both sides by 2 on the right side? What'd you do?
Yeah.
Okay, so if you do that, you end up with 2y is equal to t. And then the other one, you can write by substitution, x equals 2y quantity squared minus 2. So x equals 4y squared minus 2. I think that's probably a pretty good representation of it. And isn't that a sideways parabola? Right? It's been shifted left 2. You can see the shifting on the graph. It's been shifted left 2. And that coefficient of 4 makes it be pretty skinny on like a horizontal dimension there. And so that would seem to kind of hopefully go pretty well with the graph. Again, you could try this on the calculator. I felt like we did that a lot yesterday. You made bouncing balls and everything. So this probably would not be that difficult for you to plug and chug. All right, do you guys have any questions? Okay, so I think what I'll do is I will save that final one, this one right here, number 4. I'll save this. Maybe we'll do that as like a warm-up tomorrow or something. I would like to get onto the calculus of this. And yesterday we talked about this a little bit. Here we go. We started off by talking about the slope of a curve, or the slope of the tangent line on one of these parametric curves is given by this right here. We did talk real briefly about how this works, so I'll just remind you of this. What you can simply do here to see how the symbols work is to do a copy dot flock, right? So you can say dy dx equals dy dt times dt dx, and the dt's cancel out. You end up with dy dx. So we'll do some practicing with that here in a little bit. The second derivative, this one is a little bit harder to remember, is given by this relationship right here. And, whoops, there we go. This is maybe different than you would think, right? So let me show you what the second derivative isn't. You'd look up here and you'd say, well, if the first derivative is that, then maybe the second derivative would equal maybe this. Do you see why somebody might think that? Just differentiate the top again, differentiate the bottom again, and surely that will work out. It doesn't quite work out that way, so let me show you how it works out. So if we focus in on this, and we do some manipulation with the symbols again, right? So what I'm going to do is I'm going to say d dt of dy dx, and then I'm going to take that denominator, and just like we did with the previous one, I'm going to do a little copy dot flop. Dt dx being multiplied. We start to look at some cancellations. You can maybe see how these cancellations will work. This dt would cancel with that dt, and that's it as far as cancellation goes. So then you think about, then this is actually where the notation comes from. Have you ever wondered why it's d squared in the top and then the dx squared in the bottom, like why the squared is in two different spots? This is why. If you think about the top here, it's d of dy. It's d of dy. That would give you kind of like a d squared y. Make sense? And in the bottom, you've got a dx and a dx. So technically, it'd be like parentheses dx squared. But as mathematicians go, we will tend to get by with what we can, and so we usually just write it as d squared y over dx squared, not really understanding whether it's quantity dx squared or just the x is squared or whatever. It's from a symbolic notation, that's what's going on. If you tried to do it that other way, you end up with all kinds, it just doesn't work out, right? The symbols don't end up getting to the right places using this, the symbols do. One thing I want you to note here, as you guys know, like you probably would understand this pretty easily. To get the second derivative, don't you just differentiate the first derivative, essentially, right? And so where the confusion comes into play is when you do this first derivative, you use this dx dt, don't you? You do dy dt over dx dt. To find the second derivative, you use the same dx dt. Like that's the same in both. You simply divide by the dx dt that you used to get the first derivative, you divide by that same thing to get the second derivative instead of something different. That's where people think, well, surely I should have to differentiate that to use it. No, you just leave it alone. That's how the symbols work out, right? You copy dot flop and cancel and manipulate accordingly, that you end up with the thing that you want. Okay? So let's do some examples with this, I think, if that's what's coming up next. Yes. So let's take a look at number one. Number one, there we go, gives us parametric equations there, and it wants to know what dy dx is and what the second derivative is as well. So to get the first derivative, we would write dy dx equals, and we'd simply write dy dt over dx dt. So dy dt would be 6t minus 2, and dx dt would be t to the negative 1/2. Make sense? Okay. And then I know that you don't have to often do this. I think it's going to be very, very beneficial for you to do this, and that is to simplify. Like take just a minute and simplify this out. So this will equal 6t minus 2 times t to the 1/2. And that will give you, of course, 6t to the 3/2 minus 2t to the 1/2. You don't have to do that, but especially if you got to do the second thing we're going to do up here, it's going to make it a lot easier to simplify. So please, please consider that. I know that often with free responses we say, hey, you don't have to simplify, don't. And I think that advice still stands, but in cases like this, I think it's probably going to be very beneficial. It's not just busy work. It'd be very beneficial for you to simplify. Okay, do you guys have any questions on that part? Okay, and then the second derivative. what we do, if we follow that formula above that I hope makes sense, what we're going to do is we're going to do ddt of what we just got. We're going to do ddt of dy dx. Maybe I'll write this out. ddt of dy dx all over dx dt. So as far as a formula goes, can't I just do this right away? I know that dx dt from before is t to the negative 1/2. I don't have to manipulate that or change that, or I don't have to do anything to that. But I do have to do some stuff in the top. So I'm going to do ddt of the first derivative, and there's the first derivative right there. So the ddt of that would be 9 t to the 1/2 minus t to the negative 1/2. And as I said before, it might be beneficial, especially if we were going to do something with this, it might be very beneficial to simplify it. And so I'm going to do that. If I wanted to simplify this, I would flip up and I would get 9t minus 1. Actually is very simplifiable, right? So 9t minus 1 would be your second derivative. There's all kinds of things you could do with this, right? So based on you having the second derivative, couldn't I ask you about the concavity of the curve at a spot or on an interval? I could also ask you for inflection points. The fact that you have the dy dx right there, I could ask you about minimums and maximums, high points, low points, farther right points, farther left points, right? Think about the graph we just did. Couldn't I have asked you, I could really, on the previous graph, the one we did just a few minutes ago, I really could not have asked you for a relative min or max, right? I could have, but you would have said there are none. But couldn't I have asked you for a leftmost point? And that first derivative would help us to find that leftmost point. Okay. We good with the basics there? Is that okay? Are there any questions? No questions? Yes, ma'am.
How does that help you find the left point?
How would that help you find the left point? Okay, so a leftmost point would only happen at a vertical tangent line, right?
Yeah.
Whereas a high point or a low point would happen at a horizontal tangent line. So what I could do if I wanted to do what I just said, and I don't know how it would work exactly with this, but if I was asked for a leftmost point or a rightmost point, I would ask myself, where does this first derivative, where does it equal 0 or perhaps dne? And I think the dne on this particular example is not going to come into play. I don't see any denominators that could end up being 0. But I can definitely see where this could be a 0, right? So I don't think this works here. But what I could do is I could factor out a t to the 1/2, which would leave me with 6t minus 2 equals 0. And that would, solving that equation would give me t equals 0 or t equals 1/3. So when t equals 0 or t equals 1/3, that's when the first derivative is 0. So that's a potential high point, vertically speaking, or a potential low point. I could then do a first derivative test, or since I got the second derivative, I could just do a second derivative test and determine whether I've got a high point or a low point there. I would say often these types of situations, you'll have a domain, like it'll say t has to be between like -5 and 6 or something like that. So if that's the case, you could just make a little table, right? You could make a table and say, well, when t is this, this, and this, the y's are this, that, and that, and then make a judgment there. Am I being too vague, or does that make sense?
No.
So this would be the, like, really honestly, even though we were talking about t's and x's and y's instead of just x's and y's, the procedure for finding a min or a max or a left or a rightmost point would be the same. You'd find a first derivative, use this first derivative test or second derivative test, or a table if you've got a domain with endpoints. And we'll do that. We'll do that, yeah. Okay, so with number 2, I want to make a really big point about this because sometimes this is a point of confusion. Notice what it says. The instructions should look super familiar, regardless of the fact that we're doing some different stuff. I hope the instructions look familiar. It says, write an equation of the tangent line to the curve, blah, blah, blah. So I want to point something out. It's really important for you guys to get. To find the equation of the tangent line, you got to have those two things, right? What are those two things you got to have? point of tangency and slope of the tangent line, right? So if I've got those two things, I should be golden, right? You just go plug, 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 point, slope, and you're done, right? Here's the thing I want to emphasize to you guys. No matter what we're talking about, whether we are talking about t's or later on r's and thetas, no matter, listen, this is really important. No matter what the variables are, the slope of the tangent line is always dy dx. So whether you've got t's, r's, thetas, or God only knows what, other stuff, no matter what you've got, the slope of the tangent line will always be represented by dy dx. And so you'll want to have to, like in this case, it's actually going to be really easy because it's already related for you, but you have to relate everything back to x and y. Right? So you might have r's and thetas, I'm talking about polar, maybe, right? You got r's and thetas. In order to find the slope of the tangent line, you got to relate the r's and the thetas back to x's and y's. Because the slope of the tangent line is always dy dx. It's never anything else. Okay? So here, I mean, you've already got x's and y's related to the t's, and so that relating thing is not going to be very hard to do. But at other times, it may be a little more challenging to do. So when it says find the equation of the tangent line, you got to find dy dx at the point we care about, as well as the point of tangency. So hopefully I've related this enough to the old stuff that you know, or you can try this one. Will you guys try it? Oh, we'll see. Hopefully you do great. If not, that's okay. We're still working on it. So in order to find the equation of the tangent line, you got to find dy dx first. Dy dx for this one would be 4 cosine of t divided by negative 4 sine of t. And then when you evaluate this at our t value, so it would be dy dx at t equals 3 pi over 4. You end up with 4 times, and let's see here, cosine of...
3 cosine.
What? Oh, doggone it, 3 cosine. Struggling here. There we go, 3 times. And so cosine of 3 pi over 4 is one of those root 2 over 2s, but it's in the second quadrant, so it's negative. So negative root 2 over 2. And then down here we've got negative 4 times sine of 3 pi over 4. Again, it's a root 2 over 2, but it's positive because we're in the second. Bottom line is those root 2 over 2s will cancel, but the negatives will also cancel, so we end up with positive 3/4 for our tangent line slope. Any questions there? Okay. So then you actually have to spend a little bit of time figuring out the x and the y for the point of tangency, because the point of tangency is not t equals 3 pi over 4. It's going to be the x and the y when t equals 3 pi over 4. So for the point of tangency, x would equal 4 times cosine of 3 pi over 4, and that would be x equals 4 times negative root 2 over 2. And then for the y, it would be y equals 3 sine of 3 pi over 4. So that would be y equals 3 times positive root 2 over 2. Once we've got that, we basically have our point of tangency and our slope. We just need to put it in that point slope form. So it would be y minus 3 root 2 over 2 is equal to 3/4 times x plus, I guess, 2 root 2 if you want to cancel out the 4 and the 2. Okay, so at this point, just want to point out that this is a regular old line, isn't it? Right? It's nothing special, nothing fancy, because we're doing parametric. It's just the equation of a tangent line, just like you would have done last year or last September or whenever it was. So don't let the fact that there's x's, y's, and t's make you do something different. It's still just this. Okay? I see from your faces that this worked out just fine. Great. Okay, cool. Let's take a look at number 3. Okay, so number 3, find all points of horizontal and vertical tangency. I've been hinting at this a little bit. Given the parametric equations for x and y right there. So let's start off with this. Let's just take this one step at a time. Will you guys please find dy dx? Because dy dx is going to be the key to telling us where we've got vertical tangent lines or where we have horizontal tangent lines. So find that first. I'll do the same thing up here. Okay. Good? dy dt over dx dt. All right, so here's how we find it asks for horizontal first. So here's how we find a horizontal tangent line. So for horizontals will happen when dy dt equals 0. Guys, this is really important you get this. Dy dt equals 0 and dx dt doesn't equal 0. So in order to have a horizontal tangent line, dy dt's got to be 0, which is probably expected. But dx dt can't be 0 at the same time. All right, so with this one, what I would do is say, all right, if I'm looking for a horizontal tangent line, I'm going to go ahead and set my numerator, my dy dt, equal to 0. So that would be 2t minus 3 is equal to 0. Obviously, that's very easy to solve. T equals 3/2. So I'm going to kind of hold that in reserve here and think, okay, that's probably the time when I've got my horizontal tangent line. I might do something else with that here in just a little bit, but I need to check to make sure that dx dt is not also 0 at that point. So I'm going to just do a quick check. I'm sure you can do this without doing a whole lot of work, but I'm going to say, all right, well then, I'll do dx dt. So dx dt at t equals 3/2. And of course, I'm talking about this. So that would be 4, wouldn't it? And importantly, that's not 0. So then my conclusion would be t equals 3/2. That would be when I've got a horizontal tangent line. And I'll usually, it doesn't really specify here. I will definitely specify in quizzes and tests whether I want t values or x's and y's. And this did say points. It didn't say times. And so I would say we probably want to put xy for this. So t equals 3/2. That is when we have a horizontal tangent line. But the point where we've got this horizontal tangent line would be, let's see here, it'd be 9/4 plus 3/2, so 15/4. I'm just plugging back into my x equation. And then, let's see here, it'd be 9/4 minus 9/2, negative 9/4 plus 20/4. I'm getting 11/4. You guys know what I'm doing? I'm plugging, did I do it right? 11/4? Okay. 18/4 is negative 9/4 plus 20/4 is 11/4. Yeah, I think so. Well, you guys double check me just to make sure we don't put a bad video up there. Bad number. Okay, good. Thank you. Okay, so t equals 3/2. That's the time when it happens. And then 15/4 comma 11/4. That is the point where, like on the graph, where we actually have a horizontal tangent line. Okay. So then for vertical tangent lines, I'm sure you can guess how this is going to go. For a vertical tangent line, what we're looking for is where dx dt equals 0 and dy dt doesn't equal 0. So a good way to start this would be to set the denominator, which is 2t plus 1 equal to 0. Of course, that gives us t equals negative 1/2. And we know from before that dy dt is not going to equal 0 there. So dy dt at t equals negative 1/2 would equal 1/4 plus 6/4, 7/4. So 27/4, I think. Importantly, not 0. So if both dy dt and dx dt, if they both equal 0 at the same time, you have contradicting thoughts there, right? One of them is saying you've got a vertical tangent line, and the other one is saying you've got a horizontal tangent line. You can't have that, right? So often what the case is you have a sharp point right there. I know for sure, like, you remember from polar graphing, you remember those cardioids? They look, well, they look like that. And so right here, you would find like it wouldn't be, it would be like dy d theta and dx d theta would both equal 0 at the same time. So you'd have a sharp point. A sharp point is often what happens right there, because you can't have a vertical and a,
So do you get that on the AP test? You just
you'd say neither. Yeah, neither. Yep. Yeah, exactly.
Mr. Anderson,
Or if you get one of those on my test, you'd say neither. Yes.
Quinn, I have a question about why dy dt equals 27/4.
Oh, I just did that real quick in my head. Did I do it wrong?
Well, I got -4.
yeah, because
Doggone it.
in the original and not the differential. Because it'd just be 2 times -1/2 -3, right?
Yeah. I plugged it in the original. I even circled it right there. Yeah. I do that on the other one too?
No.
No, okay. Yep, that's what I did. Okay, so let's fix that. I know it doesn't equal 0, so that's good. So -1/2 would be, yeah, -4, right? Thank you. Okay, so again, we'd want to find the point where this happens because it does say point, not time. And so I'm going to plug that -1/2. I guess 27/4 maybe is the y-coordinate, isn't it? If I did that part right. Let's find out. So if I plug a -1/2 back into the original x, I would get 1/4 minus 1/2. So that would be -1/4, comma, and it would be 1/4 plus 6/4. So yeah, so that was 27/4. So that's the y-coordinate for the point of tangency. So it was an important number, I just put it in the wrong spot. All right. Okay, so some important things to take away here. There's differences between t, x, and y, right? And I feel like maybe you're picking those up okay, am I right? T means something important, x and y also means something important. We just want to keep their meanings straight. So let's see here. Are we really coming up against our time here?
Yeah.
Is that really, say it ain't so. You guys doing okay? Do you have any questions on this one? Okay. So let's look at what we've got left here. I think we just have, yep, this is going to work out just fine. So tomorrow, I want to make a connection here with you. Tomorrow what we're going to do, it's going to be really simple. So I want to point out a couple of things we could do with tomorrow. Tomorrow, I think what we'll do is we will open up with this one. We'll graph one more time. So, you know, that hopefully will be pretty straightforward for you. Just take your time. And then we've got 4, 5, and 6 are all related here to what we've been doing today. You see the length of a curve. Does that formula look at all familiar to you?
Yeah.
What does it look like?
The arc length.
Yeah, it looks like arc length. And if you think about it, length of a curve, we're talking about the same thing. But this is in parametric form, so it is a little bit different. We'll talk about that a little bit. And then we'll come around to kind of where we were a few minutes ago, finding a leftmost point, finding a highest point, and how that could work. And we could look at graphs with those as well. So anyway, that'll leave us, since tomorrow's our long class, that'll leave us with plenty of time at the end, guys. You've got 2 homeworks here, right? And so if you have not done those, tomorrow, the last half-ish of class, something like that, should be a good time for you to bring those in, and we can work on those and or ask various questions on this kind of thing. So I think we're in good shape to finish comfortably tomorrow. So have a great day. Stay warm.